All right. Good afternoon, everyone. Nice of you all to join me. So today we're going to be finishing up capacitance, looking at some different calculations for capacitors, and then we're going to start talking more about current. I did mention current last time, but we're going to talk more about current and get into how that's going to work in different circuits. Okay, so let's get started. So we have, I believe it was sample problem B, and then going into there, it was 1 to 3. And each of those, I think, are fairly similar to the practice one that we did before. Okay, so let's just hop right into it. I don't think they probably gave you guys too much trouble, except sometimes you can get a little bit messed up with some of those prefixes and units and all that kind of stuff. All right, so number 1. We have a 4 microfarad capacitor, and so that's going to be the capacitance of this particular capacitor. It's connected to a 12-volt battery, so that's going to be our voltage in this case, 12 volts. And we want to know what is the charge on each plate of the capacitor. All right, and so what we're solving for, so the charge on each plate is going to be Q. And remember, the charge on each plate should be the same in all of these cases. So we have for A, so the charge for each plate, that's going to be from the equation C equals Q over delta V. And we're solving now for Q, so we multiply both sides of the equation by delta V, giving us Q equals C delta V, which is simply going to be multiplying these two things together. Okay, and we can just leave it like that is and make it into micro coulombs. So here we go. So the Q is C delta V, and that's going to be 4 microfarads times our 12 volts. And like I said, we can just leave that. So 4 times 12 is going to be 48, and we can leave this as micro coulombs, remembering that the charged unit is going to be coulombs here. Now, if you want, you can go ahead and make this, this is going to be 4 times 10 to the minus 6 farads times 12 volts, and you're going to get out, what is it, 4.8, and I think we have 3 sig figs here, 4.80 times 10 to the minus 5th coulomb. So either way, it's fine, okay? So you can leave it as 48 micro, or you can leave it as 4.8 times 10 to the minus 6. So please, okay, yeah, this will be saved. This is going to be saved forever. It's up on my YouTube channel. So don't worry about that. If you can't watch now, yeah, just go back on YouTube and it'll be saved. I've got all my live streams up there. All right, B. If this same capacitor, so same capacitor, which means we have the same capacitance, is connected to a 1.5 volt battery. So now what are we doing? We're going to change the voltage. So we have a, let's see, a delta V of 12 volts. How much electrical potential energy is stored in this case? So obviously it's going to be, I'm sorry, I was looking at the wrong one. So this is going to be a delta V of 1.5 volts, right? So before it was 12 volts, and now it's going to be 1.5 volts. And so this is going to be a smaller amount. And so we still have the same capacitance. That hasn't changed, still 4 microfarads. And so what's happening now is we're going to be calculating the potential energy. Now we have a few different equations for potential energy, but the main one is just going to be 1/2 Q delta V, and we don't have the charge. Now the charge in this case is going to be different, and we can go ahead and calculate the charge, but there's no need to. Instead, we can rearrange this and remove this Q. So we have the C and we have V, so we can go ahead and substitute in, and so let's do that. So if we have an equation right here, right this is our equation for Q, and what we can do is we can just plug this right down into this equation for Q, and that's going to get us the potential energy is going to be 1/2 C delta V times delta V, so it's going to be your delta V squared. All right, and that's going to be a way that we can calculate the potential energy stored in this particular capacitor. So that's going to be 1/2 times the capacitance of 4 microfarads times, in this case, 1.5 volts squared. And let's go ahead and do that. All right, you have to be careful if anything in here is, for example, squared. If you have an exponent over here, then you're going to need to make sure that you square that prefix too. In this case, you don't have that case, right? It's the 1.5 volts that are being squared. So you don't really need to worry about that situation here. And so you can just carry that prefix forward. But you do need to be careful about that when doing this math, that sometimes if this is squared, then that's going to affect things. All right. So let's just plug it in straightforward. So 0.5 times 4, and we're going to leave the micro there with us, times 1.5 squared, and this is going to be 4.5. This is what? This is 4.5, in this case, microjoules. So a fairly small amount of energy that's going to be stored in that case. All right, questions so far? Are we good? All right. So let's move on to number 2, which is a parallel plate capacitor that has a charge. So now instead of knowing the capacitance, they're giving us the charge. So Q is 6.0 microcoulombs when charged by a potential difference. So we have the voltage of 1.25 volts. And we want to first find its capacitance. Well, we have the equation right there. C is Q over delta V. And we're just going to plug it in. So Q is 6 microcoulombs and delta V is 1.25 volts. And we're going to get 6 divided by 1.25 is going to give us 4.8. 4.8. Again, we have to be careful about these prefixes, but in this case, the prefix is on the top. If it was on the bottom, that's going to change things, right? But because it's on the top, we can carry it over, right? And so this is going to be micro what? Well, this is a capacitance, and so it's going to be microfarads, so 4.8 microfarads. Okay? All right, B. How much electrical potential energy is stored when this capacitor is connected to a 1.5 volt battery? And so this time we have, once again, a change in the voltage. So our voltage is 1.5 volts, and our capacitance is not going to change. The Q is going to change, but the capacitance is not, because the capacitor has a constant capacitance regardless of what the charge or the voltage is. So this should be 4.8 microfarads. All right? And so we want an equation. So what's our potential energy? We have the potential energy. Once again, we're just going to go ahead and use this same equation that we have here because we know the capacitance and we know the voltage. So that's going to be simply 1/2 C delta V squared, or 1/2. C is 4.8 microfarads times 1.5 volts squared. Right. Excuse me. Okay. It's going to be 0.5 times 4.8, and we're going to leave this prefix just like that, or you can do times 10 to the minus 6, which is fine either way, times 1.5 squared, and that's going to get us 5.4. And we can go back up here and say, okay, here we got 4.5, here we're getting 5.4, and it makes sense because this is just a little bit larger, so they should be similar numbers, and they are. So 5.4 microjoules. Right, questions so far? Questions? Okay. Number 3. So we're almost done here. Oh, okay. For 1B, why can't we use the Q we found in 1A? For 1B, you can't use the Q you found in 1A because you're changing the voltage. So the voltage, well, what's going to stay the same in all these, if you have the same device, you have the same capacitor, the capacitance is going to stay the same, right? So that's going to stay the same. But when you change the voltage, that's going to affect the charge, right? The greater the voltage, the higher the charge. So, and you can just imagine putting a more powerful battery on a particular capacitor is going to give it a greater charge, okay? And so that's going to change, right? The charge will change depending on what the voltage is. These two are dependent. And so in 1B, when we switch to 1.5 volt battery, we're just giving a weaker battery. We can go back and calculate what's the Q in that case, and we can use this equation, Q equals C delta V, and find out, okay, the Q is actually smaller because it's going to be 4 times 1.5, which is going to be, what, 6. So it's going to be 6 microcoulombs rather than 48. So it's a lot less. Cool? All right. So the key here, I think, to recognize is what stays the same, and that is the capacitance. In all of these, the capacitance, so when you're going down to B, this capacitance is what stays the same. All right. The voltage, as you look at this equation, the charge and the voltage, these are the two things that will change. As you increase the voltage, you increase the charge, and as you decrease the voltage, you decrease the charge. All right, number 3, we have another capacitor, and only this time, the capacitance is extremely small, 2 picofarads, which is a ridiculously small number. But it's certainly reasonable if you've got a fairly, small device. Okay, and so what's the potential difference in A? What potential difference, so we're trying to solve for that, would be required to store 18 picocoulombs. So this 18 picocoulombs, notice we have the same prefix here, is what? Well, coulombs we know, and I know this can be a little confusing because C is capacitance and C is also coulombs, but your coulombs refer to your charge, okay? So your charge is 18 picocoulombs and your capacitance is 2 picofarads. So oftentimes in science, you'll get things where you have similar letters and it gets really confusing, but just keep in mind whether it's a variable or a unit, because yeah. And then you've got voltage where the variable and the unit are the same. So we get it all. I'm sorry. I'm just sorry. All right, anyway, so on to the problem. We're solving for the potential difference. And so we have the equation from before where you have capacitance is the charge over the delta V, and anytime you see an equation that's in this form, you can simply just switch these two. So you can simply straight away make it delta V equals Q over C, all right? Or we could do it stepwise, and I can show you how that works. So we multiply both sides by delta V, so it's going to be C delta V equals Q, but we want to solve for delta V, so delta V is going to be Q over C. All right, there we go. Let's go ahead and plug in some numbers. We have a charge of 18 picocoulombs. We have a capacitance of 2 picofarads. We don't even need a calculator. Now this is again where these units are tricky. But remember, pico is 10 to the minus 12th, and pico is 10 to the minus 12th. Or even if you forget, notice you have pico over pico. So the pico over pico cancels out, right? And so this is literally equal to the same thing as 18 coulombs over 2 farads. This is the same thing, right? The pico over pico cancel, right? And so you simply now have 18 divided by 2, which is 9. And a coulomb per farad is going to be volts. So this is 9, a 9-volt battery. There you go, 9-volt battery in 3A. All right, moving on. Oh, question here. I'm just looking over before we go to B. What about the potential energy's 1/2 Q delta V equation? Is that applicable here? Yeah, it's applicable for any of these. So whichever one you want, this potential energy is 1/2 Q delta V. This is going to be kind of your go-to potential energy equation, simply because that's your potential energy that's stored in a capacitor. However, you don't always have those. You could solve for Q or you could solve for V, right? But sometimes it's easier to, let's say, substitute in something. So in this case, so in number 1, we didn't have Q. 1B, we didn't have Q, so we just substituted in and we got this equation. Mathematically, they're exactly the same equation, okay? They're exactly the same. But, and you can do any kind of rearranging to just get that for whatever your situation is. And I think there's a variety of other substituted ones depending on which variables you have and which variables you don't have. Okay, but why do we use, so we used 1/2, we used this one simply because we didn't have Q, right? So if we didn't have Q, we just had delta V and C, we have two options. Either we first solve for Q or we substitute for Q. And we know what Q is because Q is C delta V. So I just plugged it in. Well, plugging it in, right, so that gives us potential energy is 1/2. Well, Q is what? Q is C delta V, and this is all times delta V. And that's where you come up with this equation, right? PE is 1/2 C delta V squared. Delta V times delta V is delta V squared. And so that's where this equation came from. All right, but you can do it either way. You can first solve for Q, or you can do what I did and use this substituted equation. Either way is fine. All right, so let's see. And the same thing goes down here. Let's see, where are we? I'm having trouble. My playback's not working, so I'm going to go ahead and refresh that. And let's go ahead and look at, let me see here, skip this ad. All right, 3B, what's going on? How much charge is stored? So in 3B, we're actually solving for charge, right? How much charge is stored when the potential difference, so we know potential difference is 2.5 volts. And it doesn't specify it immediately in 3B, but I believe we're assuming this is exactly the same capacitor because it's still number 3, right? So our capacitance is still going to be 2 picofarads. So now we're going to be solving for your Q when you have these things, right? Just making sure. So how much charge and the potential difference and this. Yes. And so what we're going to do is we don't need potential energy in this case, but we're going to just rearrange this equation once again. So we're solving for Q, and so if C equals Q over delta V, that means that Q equals C times delta V, the same equation that we used way back on number 1A. So, yep, that's right. So Q equals C, which is 2 picofarads times 2.5 volts. All right, which means we have our pico here and no particular prefix here, so it's simply going to be 2 times 2.5, which is 5. We're going to keep the pico prefix, and in this case is going to be pico coulombs. And that's it. Okay? So, any questions at all before we go on to the new stuff? So I think we're going to be doing, I think this is going to be our last week, I think, of doing some new stuff. We're going to talk about current today. We're going to talk about voltage. We're going to talk about Ohm's law. And then on Friday, I think we'll probably talk about power. I don't know, Mr. Cody had gotten into circuits and all that, so but he skipped some of this, so I don't know. We could get into that, but you know, the year's running down. So I think what we're going to do is on Friday, we're going to talk about electrical power and then just end it there. So we can do some review Monday and Tuesday and be done, have a test Wednesday. Okay? If you guys want to do more stuff, we can do more stuff on Monday, but I doubt that anybody's going to be complaining and saying we need to do more stuff. All right, and we can always push the test back till Friday, but that gets a little bit too close to call. So in case you guys really, really, really want to do more stuff on Monday, I think we're going to shoot for a test on Wednesday. Anybody have any objections to that? Just tell me in the comment section that we need to do more stuff, and I'll do it. Otherwise, no. We'll just shoot for tests on Wednesday and finish up the new stuff on Friday. All right, so let's get on to it. New stuff. All right, so today, the goal is to talk about current and really understand, well, what is current? And then also get into Ohm's law, and I'll write that down here in a little bit. So current is got, and obviously, we already have C is being used for capacitance and coulombs. So you might think current, well, that really can't be a C, and it's not, because there's too many C's already in this electricity unit. So current is I. Why is it I? I have no idea. I literally don't know why it's I. Okay, so current is I. All right, and current has a particular definition. So current is essentially the flow of electricity, or specifically the flow of electrical charge. Okay, if you don't have any flow, if you just have charge, you have no current. Current has to be flowing. Think of, let's say, again, the whole water analogy, right? It's like water, okay? If water is flowing, you have current. We even use the same exact word in English, current for electrical current and current for water, right? So if you have flow, you have current. And the more water flowing, so, right, just like water, okay, more water flowing equals more current. Or faster water equals more current. Both things are going to increase the current. So making the water faster or more abundant, a greater volume or greater mass, is going to increase the current either way. The exact same thing is true for your electrical current. All right, and so electrical current has the following equation. All right, so I is going to equal Q over T, and we already know these two variables. All right, so I is going to be current. Q is charge, the electrical charge in coulombs, and T is going to be time, typically in seconds. All right, and so your units are going to be coulombs per second, right? And 1 coulomb per second is defined as 1 ampere, or 1 amp. And oftentimes when you're dealing with circuits, you'll have less than 1 amp. So milliamps is a very common amount of current, milliamps. But if you have a large amount of current, you can have it in amps. And any large amount of current is going to be fairly dangerous. So the larger amount of current, the more dangerous something is. All right. So we're going to be talking about current, and you know what? I'm going to talk about the other equation first before we get into sample problems. So let's go ahead and do that. And the other thing that I want to mention is known as Ohm's law. I think this is how you spell the guy's name. Ohm's law. All right, Ohm's law is an equation that relates your voltage with current and resistance. So voltage equals your current times R. And I'm going to stop using the whole delta thing. We don't need to use delta every single time we do your voltage. Okay, so this is your voltage. And we've talked about voltage before and said, well, okay, voltage is kind of like this electrical potential. And we think about it sort of kind of like a cliff, right? The higher your cliff, the greater your gravitational potential, and the higher this voltage difference, that the greater that desire, if you will, for the electrical current to flow. But you don't have to have any current in order to have voltage, or you just have to have the cliff. Once you have water flowing, that's going to be your current, right? We know the current. Now this R, well, what's this? This is going to be resistance. And so resistance is going to be any kind of thing that's going to block the flow of water. And you can think of that in a whole bunch of different ways. You can think of, okay, maybe you're going to put rocks in the way, or you're going to put some kind of a screen to make it harder for the water to flow. Okay, so resistance is something that the water needs to flow through. It might even just be a restrictive valve that makes a smaller amount of water pass. So you could think of that as some sort of restriction to the flow. All right, so it limits the flow of your electricity. Okay, and sometimes you could think of this resistance as, so this is one aspect, and resistors do this, something that limits the flow of electricity, or you could think of it as a load, which is typically an electrical load, or something that uses the electricity, and that might be anything at all. So it could be a light, it could be any kind of a motor or any kind of device. And so that's going to have a certain amount of resistance in it. It's going to be using electricity, and when it uses that electricity, it's going to slow it down. It's going to resist the flow. You can think of it sort of kind of like, like a water mill, or how a water mill would be spinning around. It's going to actually slow down that water as it goes, and it's going to resist the flow, but it's going to use it at the same time. So either that resistance is something that just simply limits the flow, or it limits it and uses it at the same time. All right, so this is Ohm's law. It relates your voltage with your current and your resistance, and is perhaps one of the most important equations for electronics, most basic equations, that is. Right? Your voltage, we already know, your voltage is going to be in volts, your current is going to be in amps, and your resistance is going to be in this thing right here. And those are called ohms. Ohms. All right? And so we're going to write it. I think that's the Greek capital omega. No, is that omega? I don't remember. What is that? I think that's a Greek capital omega. Tell me if I'm wrong, or tell me if I'm right too. I don't remember. I'm forgetting my Greek now. But I think that's the Greek capital omega, or something like that. All right? So those are your ohms. So let's go ahead and solve some sample problems. Today for homework, you guys are actually going to be doing both 17C and D. Yes, so somebody says I'm right about the Greek. Good. All right, so let's go ahead. So today we're going to be doing 17C and 17D. All right, and for 17C, I'm going to give you guys just a couple problems. So numbers 1, not 1, 2, 4, but 1 and 4. So just two problems there. And for 17D, we're going to do numbers 2, 4, and 5. So a total of 5 problems that I'm going to give you guys to do. Okay, so let's look at sample problems C and D, and then we'll be done. All right, and they are on page, let me see if I can find it. So flipping through. Page 969. 969, and let's do that. So in page 969, we have our sample problem, and I'm just going to jump into it. It says the current in a light bulb is 0.8, so let me just write it. Current in light bulb, that is current in light bulb is 0.835 amps. And we want to know how long does it take. So we're solving for time for a total charge of 1.67 coulombs to pass through. Okay, which is kind of a strange question. I mean, who really cares, in all honesty? But that's what it is, all right? So we're going to be solving, we're going to use, well, which equation are we going to use? All right, so let's write down what we know, what we don't know. So this is going to be our current. So I is 0.835 amps. We have a charge of this. So this is going to be our Q of 1.67 coulombs. And it's saying how long. So we're solving for time. Right, solving for time. So which equation relates I, Q, and T? Well, that's going to be the equation for current. And that is I equals Q over T. But in this case, we're solving for T. So you could simply just switch the I and the T. All right, mathematically, that's always going to work. Or we could just do it 2 steps, and I'll show you guys. So this is going to be I, T equals Q. It equals Q. And then T, therefore, divide both sides by I equals Q over I. So that's going to be your charge of 1.67 coulombs. And we have it over this 0.835 amps. And remember, an amp is a coulomb per second. And I'm going to write that way so we can see how the units are going to cancel out. All right, so that's going to be 1.67 divided by 0.835 and done. 2. Wow, that just worked out perfectly. 2. But what are the units? Well, we notice coulombs over coulombs cancel, and we're left with per second. So the bottom of the bottom, the denominator of the denominator, turns into the numerator. So this is simply 2 seconds. 2 seconds. And that's your answer. Okay, and so you can see this is fairly straightforward, which is why then we're going to just cover 2 sections to get today, all right, rather than just do this one equation. I think it's just we can cover another equation, all right. And so we're going to go ahead and do 17D also. And so let's jump into that, which is on page 976. And that is what? That is the resistance of a steam iron. I don't even, do you guys even know what a steam iron is? So they used to iron clothing. Do you guys know about ironing clothing? I don't even know if you guys do, because everything nowadays is like wrinkle free and nobody irons clothes these days. Anyway, so yes, somebody knows. Oh, look at that. More than one person knows. What do you know? Okay. All right. Your kids are never going to know what it is, but whatever. So the resistance of a steam iron is 19 ohms. And so R equals 19 ohms. What is the current? So what is the current means we're solving for that when it is connected across a potential difference of 120 volts. And so this voltage of 120 volts, that's standard. 120 volts is your normal, when you plug something in the United States, it's normally 120 volts. Now, different countries around the world, for example, China, I believe, is 240 volts. And then, different countries around the world will do things differently. But in the US, voltage is 120 volts, okay? And that particular load, so in this case, this resistance is not just something that's limiting the flow of electricity, but it's also using it. And so we call that a load. That iron, the steam iron, has a load or resistance of 19 ohms. All right, so what do we do? So we want to figure out, okay, what is the current? So we have the overall equation, V equals I R, and we're solving for I. So if we want to solve for I, we're going to divide both sides of the equation by R. So I equals V over R. Plug in the numbers. V is 120 volts, very, very standard. Resistance is 19 ohms. Okay, and you can see the smaller your resistance, the greater the current and the greater amount of electrical power that we're going to be using. We'll talk about electrical power next time. We have 120 divided by 19 is 6.3. That's a lot of amps. 6.3 and yeah, 6.3 amps or coulombs per second. Okay, which is a lot. But you know, your old time steam irons, they need to heat up pretty quickly, which is why they use so much current. Now, of course, they're not going to continuously use that much. As soon as they heat up, they'll probably turn off. They'll have some mechanism which turns on and off, basically based on their temperature. But that's it. All right, so we're done for today. And I'm just going to pause here and say, do you guys have any questions? Do you prefer an iron or a steamer? An iron or a steamer? I don't, neither. I do nothing, I put my clothes on and boom, that's it. I try to always buy wrinkle-free if it's something like a dress shirt. We don't even own a steamer or an iron. Yeah. So, sorry. Anyway, that is it for today. Any questions? Anything at all? All right, you guys got 5 homework problems. I think I've already put it up on Google Classroom. And this is what you got. Tasteful. All right. So, memories of Harvard? Harvard. Okay, cool. I don't even get that reference, but that's okay. All right, so see you guys. You guys can go ahead and chat as you like. I'm going to go. See ya.